Go with it. Okay. Hi, everyone. Good afternoon, good evening, wherever people are. My name is Ahad, and I was invited by Brain Brooks Brainery for their summer school, and they wanted me to do a webinar on quantum physics or something related to physics. I'll get on with that. About myself, I just graduated with a master's from Imperial College London in theoretical physics. And yeah, so when I got in touch with these guys about doing a webinar in physics, my specialty lies in condensed matter theory, which might not make sense to any of you right now, but I'll get on with it as we go into the talk. The whole idea of the talk today is basically to give you guys a little flavor of what the world of quantum physics looks like. Because as a kid, I imagined people reading about anything to do with quantum and being excited immediately, and that always sort of enticed me as a kid, and I just wanted to get along with that. So I'll just start sharing my screen and then we'll kick off. Right, let's go from the beginning. um can you Is the screen visible then?
Oh, it's loading.
Okay.
Yeah, it's
Yep.
visible.
All right. Right, so let's talk about this topic firstly. How quantum can it get? I think this is a question that the title of this talk is a question that I had in my mind, and I derived it from the topic of how hard it can get, as to how quantum it can get in the field of physics when I was in my second year of bachelor's. And when we talk about physics or theoretical physics, this image is probably a good representation of what people think it actually is, and it might scare a lot of people at your age as to how hard the math can be. So my whole talk today is designed about this mind map here. I think this is by far the best picture I've seen on the internet. This is not made by me, but this covers essentially every field of physics that utilizes some bit of quantum physics in it. And if I point towards the top, the pre-quantum mysteries is probably something that you might have encountered in your studies so far, but pretty much everything else apart from that may or may not be that clear now. So the whole idea of the talk is I'm going to walk you through a little bit about the history of how quantum physics sort of came around in the world. And I'm just going to walk you through in sort of a fairy tale story, and then I'm going to walk you a little bit through different parts of quantum physics in very layman terms. And eventually, also want to give you a little flavor of what my research or what my thesis was on. I think it's a very hard topic to get into, but I'll try to narrow it down as much as I can. So basically, before I go that, these are probably the four most favorite people that I have in terms of the quantum physics side of the world, and that's Einstein, Richard Feynman, Paul Dirac, and Niels Bohr. I assume everyone knows Einstein. Dirac was a very, very genius physicist and a mathematician. Precisely, he sort of came up with the idea of relativistic quantum mechanics, and he was just really brilliant. In fact, I have a story to tell about him as I go along, but I wanted to. But basically, I'll touch on it a little later, I guess. It'll make more sense then. All right. So let's begin. So, what led to the quantum physics revolution? So, we are at a time in history when Maxwell came up with his equations in electromagnetism. And Einstein was very hot shot at that point in special relativity. And he was coming up with the ideas of general relativity. There were two problems that classical physics could never explain at that point, or it fell short. One was the black body radiation. I assume that's something you might have covered. If not, basically, when you heat up an object, it sort of produces electromagnetic radiations, and that is what's called a black body. What you look over here in this graph is basically the blue line is what the spectrum of a black body radiation object looks like. And there were two theories that were based on classical physics. So there was this Rayleigh-Jean theory, which is the orange dotted line, and then there's a green dotted line for Wayne. But as you see, none of them come close to the actual graph over here. So at that point, the world was not quite sure as to what was happening, or why was classical physics falling short when we were talking about thermodynamics and stuff like that. Another issue was that of the photoelectric effect. And that's basically when you illuminate a metal, when you hit a light on a metal, you release electrons after you hit the light at a certain energy level. Again, this was a mystery at that point, and no one really knew the answer to this. So classical physics couldn't explain it. And that's when Max Planck, this guy over here, came into play. And what he said was basically, he came up with a new thought of an approach, which I think was remarkable at his age, is that something called the wave particle duality. You know of electrons, right? So we know that electrons are particles and then light is just a light wave. What he came up with was the fact that these electrons can basically act as a wave and as a particle both, which I think is very bizarre when you think of it. But I'll sort of get into a very cool animation to show you what I mean. So what happened was, at that point, when Hertz in 1887, they sort of saw this phenomenon of the photoelectric effect. Einstein then used Planck's idea of saying that these electrons have can act as waves and particles both to explain the photoelectric effect. And rightfully, these two earned Nobel Prizes for both of them. This equation at the bottom, E is equals to H nu, is basically signifying the energy of these electrons. So what I'm trying to portray here is that these electrons, they have discrete energy levels. So what at that point quantum mechanics was trying to establish in the world was that everything in the quantum world was sort of occurring at a discrete nature rather than a continuous nature. So like continuously you'd have a wave going through. And the best example for that would be to look at the double slit experiment. So what I've done here at the bottom is I've given you two diagrams. On the left, you see a bunch of donuts being fired from a donut gun. So let's imagine, so if you've seen what the double slit experiment looks like, is basically you're firing a particle or a wave at a slit, and the slit sort of makes these waves diffract. And if there are two slits there, they will interfere to have constructive and destructive interference, which sort of gives you a pattern. Classically, if I was to hit a single donut from the donut gun from the slit, it would either go through the top slit or the bottom slit, right? And then it would hit the screen at some point here. While on the contrary, the light source would sort of diffract from the two slits and they would combine to give you this pattern that I've seen shown here, which is called an interference pattern. But now check what happens here, right? So let me play this for you and then I'll explain what this means. So watch this carefully. Wait a minute. Right, let's play this.
It isn't being played.
It's not?
No, it's just the slide.
Oh, I just clicked play. So for me, it's playing. That's weird. Wait, let me do one thing. Oh, sorry, my screen sharing is paused for some reason.
Maybe you could exit and go on YouTube.
Yeah, does it work now?
Can you play? Are you playing it? I can just see all your slides. And
Yeah, wait a minute.
Yeah.
Yeah. Okay. Now hopefully it works.
There's no sound. Is that right?
Yeah, there's not supposed to be any sound. It's just a visual for people to see.
Okay, great.
Okay. Right. Yeah. Keep having a look and then I'll explain what I mean from this. Right. So this is a wave that's hitting the screen. And as I said, you see an interference pattern occurring on the screen. Before that, you saw a particle. Now look at this quantum object, which we can call an electron in this case. When it goes and hits the screen, right? It goes and hits the screen at a certain point. But notice the pattern that these electrons are going to make there. As this keeps moving, you notice that they make a similar interference pattern to what a wave made. Now, this is a bizarre thing to occur at this point, right? We saw what the particles did is that they just randomly hit the screen. From a wave point of view, the waves made an interference pattern on the screen, while the quantum object, which was also just particles, it made a wave pattern on the screen. Now what I do is I add an eye or an observer to it, and now check what happens to these electrons. Right, it hits. If you notice carefully at this point, you might see that there is no longer a pattern of where these electrons are being hit on the screen. So that's what basically this, look at this pattern. So it's quite random there, right? So one takeaway point from today is that electrons sort of have a consciousness. And I think it sounds bizarre when I say it, is that when no one is watching them, they can act like a wave and a particle both, depending on the situation. But as soon as one starts to observe them, they start acting as particles. They give up on their wave nature and they totally act as particles. This is something that was really, really important to understand in early quantum physics, because this is basically very crucial to a lot of various phenomena that occur in quantum physics. So before I move on, can I quickly get something in the chat if they want to see this animation again, or they want me to explain this again, because I think this is a very key idea to sort of get into before we move on.
Guys, let's have 4 to 5 answers quickly in chat. Yes, if you'd like it to be explained again. No, if we can move on.
Right. I think we can sort of push forward. Right. Let's go ahead. Right. Right. Okay. So then we come on to something that's again rather very crucial to quantum physics, and that's called the Heisenberg uncertainty principle. In a definitive manner, this is basically that if a measurement of a position of a particle is made with uncertainty, and you may make a simultaneous measurement of its momentum with its uncertainty delta p, the product of the two uncertainties can never be smaller than h bar divided by 2. Okay, that's just words and probably doesn't make sense. Basically, Heisenberg uncertainty principle brought about a really good part of quantum mechanics in establishing that you can never know a particle's position and its momentum accurately at any point in space and time. So if you know a particle's position very accurately, you would never know its momentum. And if you know the momentum of the particle, then you basically don't know its position. So it's like a mystery. And a lot of people might think here that it's probably because of the measurement instrument that you're using, but that's not the case. You can use any sort of measurement instrument that you can think of, measure the momentum or the position of the particle. The issue is that due to the quantum nature of this electron or whatever particle there is, you will never be able to do that on an accurate scale. So this was something that was again established by Heisenberg, and he won his Nobel Prize in 1933. And again, it was quite remarkable given at their age, right? Then we come on to the world of quantum mechanics. I know the maths might look a bit scary, but I just wanted to add a bit of a flavor to what quantum mechanics was in a very easy mathematical terms. So the wave function here is basically how you represent your nature of the particles, or basically the wave in quantum mechanics. There are three parts to it that I'll go through one by one. This is the amplitude, the A part of it. Then e to the I phi represents the phase of the wave or the particle. And then the last factor here is basically the time dependence of your wave function. What is a wave function? Wave function basically is just a function like in any normal real analysis. What it does is it explains what the particle does, how does it behave, and how much phase does it have, similar to how you might have done it in like standing waves or stationary waves, something like that. Now, the key point in quantum mechanics arrives in the fact that it is a probabilistic theory. So you can never be certain about where a particle is in quantum mechanics due to the Heisenberg uncertainty principle, and also because of the interference pattern that I just showed you. Hence, if you take the square, like the complex square of this wave function, that is the probability of finding the particle at any point at stage. So you can no longer be sure about where the particle is. And that's what I think makes quantum physics quite beautiful, that it's quite literally a game of probability. On the right-hand side, you see what's famously known as the Schrödinger equation. This is used as basically just a linear differential equation, which shows how the wave function transforms in the space and in time. On the bottom right, we have Mr. Schrödinger himself, I think quite a revolutionary guy in quantum mechanics. And the entire purpose of this equation is that you can put in any sort of wave function. It'll give you an idea of how this wave function behaves. And remember how I mentioned the energy discretization at the beginning of how the energy levels are fixed and quantized in quantum mechanics. That's what you get from these equations. Just to get a feel of that, let's look at two examples of two quantum mechanical systems that we have. We'll begin with a very simple one, and that's on the right. Again, my favorite donut occurs. So this donut is quite literally a free particle. It exists without any bounds, without any potentials. And you see that so we solved the Schrödinger equation. You don't need to really know the maths at this point, but know that this wave basically gives you the wave function for this free donut. And if you look at this, you might have seen this when you've done your waves course in whatever classes you really are. There's one thing remarkable that I really wanted to go into, and that's why I wrote this equation down here. So if you look at this, it's written like this is the energy of this donut in quantum mechanical terms, and the P over here represents the momentum, and M represents the mass of the donut. So P squared divided by 2M. This is all pretty much quantum mechanics. Momentum in classical regimes is known as mass times the velocity. If I was to plug that in, I would get this equation here, which pretty much looks like the classical kinetic energy, right? I think that is quite remarkable. And I, at least for me, when I was a kid, I used to be very fascinated by this, because right now what I've seen is that we just saw the emergence of classical physics from quantum physics. So quantum physics is occurring on the microscopic scale. And that's again something that quantum physics establishes, that as you go to larger systems, eventually there is a limit. It's a large number limit in which you do tend towards the classical physics. So that's something quite interesting that I wanted to touch on. From there on, there is another really interesting thing in quantum mechanics, is that in a classical image, let's say you had a barrier in front of you and a particle was to hit the barrier. It would hit the barrier and go back, right? That's what we have pretty much seen, I think, by our eyes as well. But quantum physics, again, is rather funky in that case. So if, whether you believe it or not, the electron would come through to the barrier and it would tunnel through to the barrier. Now, what do I mean by tunneling? Is quite literally that electron can pass through the barrier and go past it. So it would not entirely reflect. It can partially reflect back, but a lot of it can be transmitted through that barrier. And that's something, again, that quantum mechanics establishes very profoundly in the early eras. A lot of people ask this question when they first encounter quantum tunneling, is there actually like something in the world, in real world applicative, that uses this technique? So there's something called a scanning tunnel microscope, which actually uses quantum tunneling to perform high precision microscopies of objects. I'll see if I have an image of it and I can show it to you later on. But yeah, so these are the two examples that I really wanted to show you. Right. So that was a short recap, short sort of a story and a fairy tale of how, from what problem, from the black body radiation all the way to finding these quantum mechanical problems in the early 1900s, how was quantum mechanics transformed? From there on, what happened was Einstein came up with general relativity. People wanted a relativistic version of quantum mechanics. Paul Dirac, and I wanted to tell you this story. So when relativistic quantum mechanics, by what I mean by that is combining special relativity with the quantum mechanics to formulate a special theory, was being formulated, people could not find the equation the exact Schrodinger equation for to solve the relativistic quantum mechanics. At that point, Paul Dirac quite brilliantly came up with this idea, and he just came out of it with nowhere, is that he made an equation and he called these he had two solutions from that equation, as you might just from a like a quadratic equation, you have a positive and a negative root, right? So he got two solutions to his equation. One was a positive solution, the other one was a negative solution. So he said that, okay, fine, the positive solution represents the electron and the negative solution represents a C of something that's the opposite of electrons, right? And I think that's just like to think of it is something that's quite remarkable. But then later on, Feynman proved him wrong, and they later established that there's no C, but in fact there's a particle that's the anti-particle of the electron, the positron, that actually exists. So without having any knowledge of that, to produce that just from a raw mind in that era when these resources were not available, it's probably the most inspiring quantum physics story, or you can say even physics story, that I've ever heard. Yeah. All right. So what we covered here today was basically this pre-quantum mysteries and the quantum foundations. Quantum physics is quite vastly in depth into different parts of physics. So I just wanted to give you a little flavor of that through this mind map. One thing that's really hot and about in the world right now is quantum information and quantum technologies. Supercomputing, quantum computing is at the core of quantum physics. The idea of using a spin in particles, I don't really want to go into depth of it, is being highly hotly researched in various universities and even by companies like IBM, with the aim of making a quantum computer. There are some key problems related to it, but it has to be achieved, and I think it can be achieved. Then there is quantum technologies. I guess anywhere you go around, from microscopes to superconductors to transistors, the solid state part of physics is evolving rapidly as well. Every day we come up with new technologies, new sort of illuminations, methods, and materials. And that is something that I've been working on in my career as well. My interest basically lie in quantum technologies and condensed matter physics, which has to do with different materials and sort of utilizing the properties of these materials from a quantum physics point of view to improving different things, as such as, like, for example, I don't know if you've heard of Bose-Einstein condensates, but they are a state of matter, and they can actually be used to form something called a super solid. And that's something that's a very hot topic of research that's being done all around the world. Then, of course, there's this idea of quantum phenomena such as entanglement, teleportation. These are all being very highly researched. And again, they form a very core part of what people really want to focus in the upcoming years. So this is more what to do with modern day physics. If I go towards the other spectrum of people who really like to work in theoretical physics, and that's got to do with the idea of the theory of everything. So the theory of everything basically sort of aims to unify all the physics there is in the world to explain it in one sort of a unified theory. So in that sense, quantum physics also related to particle physics, everything that's got to do with everything they do at CERN, like antiparticles, particles, the standard model of physics, which has all the particles that there exist. From there on to quantum chemistry, nuclear physics, quantum electrodynamics, and quantum gravity. So I assume a lot of you might have heard the term of string theory. So these are all things that come together, and even in quantum field theory. But eventually, this mind map basically summarizes very comprehensively where and how quantum physics is being applied in the world right now. And I think in the next 20, 30 years, it's only going to go further and further. And I think it's a beautiful subject, because the main idea with quantum physics, and this probably will be my ending note before I take on questions, is I'll go back to my favorite scientists. In fact, they have this saying, is the main idea is this thing. Yeah. Feynman quite literally says that I think I can safely say that nobody understands quantum mechanics. And I think that's the most beautiful part of it, is that you go through such beautiful physics, whether that might be mathematically or mathematically, And the fact that it takes you a little while to absorb and also to come to terms with is what makes this field quite dynamic and quite attractive to anyone who's new in the field. And I hope this short talk, I know it wasn't really detailed because I really don't want to throw details at you or jargon at you that might scare you. But I hope I've given you a little flavor of how quantum physics looks like to the world. And yeah, from now on, I think I can take on any questions that you guys might have. And I'll go to the map if that might help people.
Great. So, guys, if you have any questions, you can put in chat or you can raise your hand. In the meanwhile, Ahad, would be all right if I read you some questions from chat.
Yeah, sure, go for it.
Okay, so there are some questions from early on that I think you might have answered, so you can just let me know if you have. But the first one is from Shubham. How, after adding an observer, does it just form random patterns? Is it observation or finding electrons?
Okay, right. Yeah, it's an interesting question. So basically, the idea of quantum mechanics is when you measure something in quantum mechanics, the particles, and I'm being in very like frank terms, it means that the particles decide that they don't want to be quantum anymore. So that's called the collapse of a wave function. So when you add an observer at that slit, what happens is that somehow, like in physics term, these particles have this consciousness of knowing that they're being watched, and that's what's called the collapse of that wave function. And they no longer act as a wave, so they lose their property of being their property of the wave particle duality there.
All right, I hope that made sense to whoever asked. Does magnetic resonance imaging use quantum physics?
No, I don't think so. I think there's something called magnetic infrared microscopes that use that, but I think, yeah, MRIs don't use quantum physics.
Okay. Let me know again if you've answered these questions already. How do you come up
Sure.
with the wave function? Is it observation?
Okay, so that's what theoretical physicists do. So there's two approaches to that. There are some systems that have analytical solutions. What do I mean by analytical solutions is that they have exact maths that can be worked out by hand. And then you can work out the wave function by just doing the maths or by solving the Schrodinger equation that I showed you. The second approach is to do these things numerically. So there's a lot of numerical approaches that exist that use programming languages such as C++, Python, that numerically solve the system to give you numerical answers to how the wave function will look like. But you can't produce it out of the blue.
Okay, great. When you say electrons are either particles or wave, do they actually look like a particle?
Well, I haven't seen an electron, so that's interesting. But yeah, they are supposed to be. So when we say they are particles, they're supposed to just be a single particle on their own. And when we say they're waves, they're supposed to be like actually just like an electromagnetic wave. So they're supposed to be in transverse direction to the motion and everything like that. Yeah.
All right. And then last one in chat, guys. Again, if you have any other questions, please put it down. But if there are none after this, then we can wind up. How does quantum biology and quantum chemistry focus on the wave-like nature of it, since biology and chemistry tend to focus on particles?
Right. So quantum chemistry, basically, in your chemistry that you might have done so far, you might have read about orbitals, right? So the whole idea of is not exactly waves, but how quantum physics come into play in quantum chemistry is that these orbitals are essentially superposition of different wave functions. So like when you use SPDF, I assume you guys might have heard of these orbitals, right? So what happens is that these, like the s orbital can be represented by a wave function. And if you've read about hybridization, hybridization is basically when you have a superposition of these particles to form atomic orbitals. So that's a very good application of where quantum chemistry has these quantum. But yeah, wave-like nature is not that implicative in quantum chemistry there.
Right.
And
yeah.
Quantum biology, that's probably the only subject on this mind map that I'm not very comfortable with, and that's precisely because I've never done biology on my own. So yeah, I'm not sure if I can answer that.
Okay, that's great. And the last one is, can you please explain the observation part in quantum mechanics again?
Sure. Let's go back to that visual. And don't worry if you don't get this. I read a comment that said, "Oh, this is so difficult." The whole part of quantum physics is it takes you about a good year or two to get in terms with. Right. So let's look at this up, and let me just go straight to this point. Okay. So observation is something, and if you want to read up on it, I can tell you, you can search up the measurement problem. So a particle acts like a wave as long as it's not being observed. What do I mean by observe is that as long as you don't make a measurement on the system. So there are various measurement instruments that you can use in an experiments to measure, let's say, the velocity of a particle, the momentum of a particle. As soon as you measure any one of these physical observables of these particles, the wave function will give you, so wave function has multiple values to it, right? And it'll give you only one value out of it, and the entire information about the rest of the wave function will be lost. So that's more mathematical. If you look at this diagram here, so in emission, if you look at the particles hitting the screen, they are all over the place as they are supposed to be, right? They're particles, they don't really have a specific pattern. Then I showed you the wave. And when you see this wave, you see a very good interference pattern, bright, dark fringes combined. Okay, then I went towards a quantum object. So this is when there is no observation being made on this quantum object. Look very carefully as how these electrons hit the screen and they form a very fringy looking pattern there. It's the same as the wave. Observation, so let's say over here, I'm observing the momentum of the particles at one of the slits, or right? So I have some sort of a detector there. When I do that, what happens to these particles is that they will regain their random nature. There you go. So in very short terms or in layman terms, whenever you try to measure a wave function, you sort of lose all the information about the wave function except the one that's being measured. So yeah, that's probably something that explains observation there.
Great. Thank you so much. And Swam has another question. How do we observe an electron as it is hard to get its momentum while finding its momentum and vice versa?
Wait, can we repeat that?
Yeah, sure. How do we observe an electron as it is hard to get its momentum while finding its position and vice versa?
Okay, yeah, so that's where the Heisenberg. So there is, so in quantum physics experiments, uh, there is something called a quantum noise limited measurement. Too much jargon, I know, but what it does is that while keeping track of the Heisenberg uncertainty principle, you can always measure the momentum of the particle, but you will lose the accuracy at its position. So like when you experimentally measure these things, you always have error bars to it, right? So you say, like, let's say you make a measurement of 5 millimeters of a distance, you have always have an error bar that would say plus minus 1 millimeter. So this error in the measurement of the position is going to increase while it would decrease for the momentum. So your momentum measurement would become more accurate, but your position measurement would become less accurate in this case.
Right, great guys. If we don't have any other questions, then I think we can wind up. Ahad, thank you so much for coming on here today. This is our first
Noise.
non-college application, non-resume, something subject specific, and we're really glad we could make this happen. Thank you so much, guys, for being here. Ahad, thank you once again, man. Any final words, thoughts before we end?
Yeah, sure. I think it's a brilliant field to get into. As always, someone who people who are in college, I always tell them is that explore yourself in physics. There's a lot you can do, and if any one of you has any interest in applying for college apps or something like that related to physics, you can always find me on LinkedIn, give me a message, and I'll be happy to help you out in whatever ways I can. That's all from me. Thank you.
Thank you so much. Okay, we have one last question if we can take it. Uh, why is quantum mechanics incompatible with general relativity?
It's not.
Okay, it is not Manjurul. Okay, thank you so much. We can end it there then. Thank you, Ahad. I'll see you soon.
All right. Thanks.